Today we continue to work on our typing trainer tool, and so far we've been able to generate our text either from a list of words, then there was a weighted list, right, where we gave some sort of weight for each word. Then last time we managed to grab lines from file, and we talked a little bit about this Markov chain option that we want to introduce in this episode, which will produce still nonsense, but it will be read as a real text. You know, sometimes you won't even understand that this is like just randomly generated thingy. If we look at Markov chain definition, explanation, you will probably be confused. There's a lot of things, some crazy math going on here, but really for our use case, it is going to be used in a quite simple way. So let me go to images and find something like Markov chain text generation, and I think like this one is a great example. So small article explaining this Markov chain usage for text generation. So pretty much what we're going to do is we're going to grab some text. It can be a book, it can be whatever text you like, it can be multiple books. We will analyze it in our case, and as this picture shows, we are gonna find all the triplets in this text, and by triplet I mean like 3 consecutive words, and we will store the first 2 words as a key, and the third word will be put into a list of what can follow those 2 initial words. Here it has a nice example saying that if first 2 words are quickly and he, then the only word that can follow it is the word ran. I mean, this example probably used a quite small text for it, but it can show you that if we have 2 words, he ran, then it can be followed by either and or until. So really, this shows like this. This shows how we can generate stuff having this pre-computed relationship of triplets. So for example, if we start with this pair of words, quickly he, we know that the only one word is ran following, so it will be quickly he ran. So now 2 words we're interested in are he ran, and here there is a list already of possible ways to continue. We pick randomly one of them. So for example, quickly he ran and he ran until he couldn't. So really this is pretty much it to Markov chain. So grab the text, split it to triplets, and store all the relationships between the pair of starting words with what kind of third word can follow that pair. Alright, so let's try and implement this thing on our site. First of all, Markov chain. This is our new config option of how we want to deal with text generation. We need to update our get text for new match case, which is Markov chain. This is going to be generate Markov chain method. We can probably grab this as our template. So now the method generate Markov chain, it has a path to a file. In our case, we'll do the easiest thing possible. So we'll just analyze a given file, a book in my case, and we will return as a result generated string. So first of all, as usual, we read the contents of the file, then we'll do something like chain build from these contents, and we will return chain generate. Okay, no semicolon. Right now we don't have this Markov chain, so it complains about it. So let's jump to our main and define new module Markov. We create it, we jump into it, and we can define a struct called Markov Chain, and alongside its implementation, which has two methods. First of all, the build one, so we have some text, and we're gonna return self, which is just a do for now. And the second method was build and generate, right, which has a string return type. If we jump back to our text module, we can now import this Markov chain, and it no longer complains. So really, this is just an entry point to our Markov chain. We read the file, the whole file, ask our Markov chain module to build this whole relationship between triplets of words, and somehow generate the text for our typing session. So let's jump right here and think what this struct should look like. First of all, as I said, we need to keep track of relationships. Given a triplet of words, we have the first two as a starting point or a key, and we will have a list of the words that can follow those initial first two words. That is why the first field is going to be transitions, which is going to be some hash map from key to pack of strings. What is a key? Let's define it locally as a pair of strings. Right, so really we're saying that transitions is a relationship between a pair of words, and it has all the possibilities, all the possible words that can follow this pair that we have actually seen in the text. And then in order to improve our text generation, we want our sentences to start only with those pair of words that we have actually seen in the text. So all the sentences, we're going to grab the first two words and put them into starters, which is going to be just a vec of keys. Right, so we could avoid using starters. We could simply analyze the text, grab all transitions, and randomly pick and use them to generate text. But then our sentences won't be started really well. It can start with something really random, pretty much as before. But if we keep track of every single sentence starter, meaning the pair of words, then each sentence that we generate ourselves, we can simply grab a pair of words from this vector. As usual, we need to derive, debug. Maybe we'll even use default here, so that when we want to build things from text, what we're going to do is we say that hey, chain is self default, and at the end we will simply return chain. And how are we going to build it? So really what we want to do is something like this. For each sentence in our text, we want to do something. Right? Unfortunately, text is just a single blob of characters, and this is the whole text and the book in our case that we're going to use as our input. So we need to somehow extract sentences from this text. For that, we're going to use a function named sentences, which is going to return vector of strings. Right? So assume we do something here that splits this whole text into sentences. So then in our build method, the sentence is a string that we can work with. So what we want to do is split the sentence into words. So words is sentence, split white space, right? Then we can do some cleanup, filter the word. We don't want to include anything that is empty, and then we collect. So we need to say that this is vec of strings, or just it will infer the type. All right, so what we're missing here is this cleanup string method. So really, when we split the sentence into words, there are going to be some characters that we either want to transform into different characters or just want to drop them completely. You'll see, like, once we implement that, it should be a very small and tiny method. So cleanup string, it will take in input, so some sort of string, and produce another string. Right. So we will get back to these two methods a bit later on. For now, we are still like building our Markov chain. So we have text as an input. We grab a sentence, or we iterate over all sentences. We split each sentence into words. Then, because we're dealing with triplets, we really don't need any sentences which are less than 3 words. So if its length is less than 3, we really can't do anything with the sentence. We can simply drop it. Now, first 2 words are the sentence starters. That's why we want to say that, hey, starters, let's push, and the value is going to be words 0 and words 1. So this is a pair. For each sentence, the first 2 words are the words which the sentence starts with, and we need to keep track of it in our chain starters. And then, because the sentence can be quite long, it can have 3 words, 10, 20, 30, we don't know. We want to analyze this sentence by triplets of words. And luckily for us, we can do it easily using a window function, I think, on container or on collection. So it will look something like this: for window in words windows. The size pretty much asks you the window, or how many elements this window should use. I think it has some example. Yeah, so if we have lorem as a collection of characters and we use windows of 3 characters, then the first slice that we get is lore, then ore, and rem. So in our case, window has 3 words, and what we want to do is we want to somehow put it into our transitions. So first of all, let's define the key as window, the first 2 words. Then transition is a hash map. We can grab its entry, right? Entry gives us an ability to in-place manipulation. by this key, and because it can actually might not be present there, we can use or default so that it creates the empty vector where we keep track of all the following words for this key, and we can simply push the window to clone. Right, let's format it, and this is pretty much it. This is how the build function looks like. Again, we have full text as an input, we split it into sentences, and we work with the sentences. For each sentence, we split it into words. If the sentence is too small, we just ignore the sentence. Then we save the first two words as a sentence starter, and then use a window of 3 words. We iterate through the whole sentence using this window of 3 words, and keep track that for these first 2 words, the third one is the one that can follow them. Alright, so let's quickly look at how we can split sentences and what we're going to do with string cleanup. Let's see. So sentences. Really, we are probably need just to say something like split. Split at, right? No, just split. Given some character. So, for example, if it's end of sentence, right? So we're just saying that what we consider to be end of sentence, right? Then we can again invoke cleanup of the string and just again filter, given that we don't want our sentences to be empty, and we return vector. So what we do is we split at this at the character, where character is just end of sentence, that we believe this is the end of sentence. This is just a tiny and simplified version. If you want it to be more production ready, you would use some library for that can produce a better split of sentences. Then, but it serves our purpose. This is enough for our use case. So what's left is really like this cleanup string, and I really don't know. Let's see, like what do we want to do here? We want to avoid having some characters that we don't want to see in our text. So for example, let's see, so string matches, trim matches, right? So really what we want to trim, it says that we are going to trim the string, so remove things from left and from its right side, prefix and suffix, given some pattern. So I think we can use this macro, right, for given pattern, so it matches. See what does it match. For example, there are some quotes, single quotes, or maybe even some underline. So if our given string has these symbols in the beginning, we really don't want to see them. We want to just trim them. And then this is probably just to string, something like that. Let me, yeah, I think this is, yeah, maybe we can add like a few more. So if our word has these symbols in the beginning or at the end, we really want to just trim them away. All right, yeah, I don't know, like whether we need space or not, but yeah, should be enough. So this is just a cleanup. This won't remove these characters from the middle of the string. So this trim matches really works as a trim. So it works with prefix and suffix. And this should be enough for our use case. So once the chain is built, we can then start generating stuff using our preprocessed data. So let's do exactly that. First of all, we need some RNG. Then we need to keep track of all the words. And probably needs to be mutable. And I think that we generated something like 100 words before for our previous use cases, so let's do exactly the same way. So while we have less than 100 words, we can generate things. And yeah, we can do, and once we generated enough words, we can then split them into chunks, right? So as before, we need to say that lines is something like words in chunks of 10. We map this chunk where we join all the words with space, right? And then we return all those lines joined by new line. So this is pretty much the same thing that we did in our previous generators. So the most interesting part happens in this while loop. Let's see what needs to be done. So first of all, we need to pick a starter, right? So we can say that starter is self starters choose given RNG, or else we can return something like default, right? We can even say some, right? So pretty much just saying that, hey, given all the starters, pick one at random, and yeah, if you fail to do so, just return default, meaning that this pair will have empty strings, but hopefully that will never happen. And first of all, this is sentence starter, so we can instantly push the starter 0 and starter 1 into our words. Yep, we need to push it one by one. Okay, so it doesn't like that. We cannot index because it's a pair. Let's do it this way. Previous current is our starter. Right, so we have like two words, string. We cannot move out, so we need to clone it. All right. So we have two words which start the sentence. And now what we're going to do is we're going to go into this loop. And first of all, we need to grab choices from our transitions map. So given transitions, we can probably get by previous and current. This is our key. Or else we can break, right? So because we are in a loop, it doesn't like all right. So choices is now our option. So what this line does is asks our transitions to find the following words of a given pair of words. So our pair is previous and current. And if it's not found, then we simply break. So, and this is actually how we exit the loop, is that we have reached a pair of words which doesn't have anything following it. So as you will see, this will probably be the ending of a sentence. So current will have some sort of thing at the end, but yeah. Don't know like whether my explanation makes sense or not, but really what we want to do right now is just given a pair of words, we want to find the list of the word that can follow it. So this is a list, and if the list is not found, then yeah, we break generating this sentence. So we don't break of this while loop yet, of this whole while loop, we're simply dropping from this sentence generation. So this while loop is pretty much generating the whole text for our typing session, while this loop is responsible, well, including this words push, is responsible for sentence generation, single sentence generation. So once we have some choices, we have next word, right? So we can, yeah, let's call it just simply next, is choices, choose, again with our random, or else we break. And if for some reason we failed to choose the word, we simply break again from our sentence generation. But luckily for us, it really should be there. We shouldn't have any empty vectors in our hash map. So the break that should actually exit the loop is this one, when we find a pair of words which doesn't have anything following it. And now that we have found the next word for our triplet, we can push it into our words. And as we are iterating in the loop, we go to the beginning of the loop again. We use the previous and current here, meaning that we need to set previous to current and current to next. And this we need to clone, and probably we can drop this clone because it never gets used anywhere else. But this one is still required, right? Because here we move the value. And this really should be it. So in our build method, we've built this structure, having the starters and transitions. And once we start generating, we are trying to generate a somewhat enough amount of words to train our typing skills on. So it can actually exceed 100 because we're generating the sentence without actually any limit here. And for sentence generation, we are really picking the starter pair of words, push it into our overall words container. Then we find all the transitions, all the words that can follow this initial pair. We pick one at random, and then we just substitute previous current so that we can generate the next word for the next triplet, and so on. If we run our thingy, we see what? We see some code from our main. This is because our config still has a file. So let's change it to something like data Markov txt. We don't have any text, but really we can just jump and download free books. Yeah, this project Gutenberg has a lot of books that are readily available for download. I think I prepared one. I think it was Alice in Wonderland. So if we open, yeah, it's Alice Adventures in Wonderland. We can probably, let's see, drop some stuff from the beginning, then there is some stuff that we don't need at the end as well. So once the book ends, the end, we can drop everything after it. So this is the whole book. You can see there are more than 3,000 lines, quite a lot of words. And now we are gonna run our trainer. And what do we see? We can instantly see that the first sentence starter is somewhat weird, borked. And yeah, it's probably because the text, let me open data, the text has these weird, right, how do you call them, not bracket, braces, brackets, braces, whatever. So let's jump into our Markov, and here in our cleanup string we want to do we want to make some adjustments. So here is the thing. So these two symbols, they have nothing to do with this one, right? So they are different, but we want to transform them. Oh, so let's do it. Let, how do we call it? Let. Yeah, let's call it just let new string is just string, given its chars. We map it. How do we map it? And collect. See, we match C. Oh my god. No. It's not exhaustive, yeah. So if it's for anything else, we just return it. All right, so what have we done here? So we've seen that there are some weird symbols, right? So this one's looks to the right, this one's looks to the left. We want to use the normal symbol so that it gets trimmed in our trim matches. If we run it again, then yeah, it seems that they disappeared. What is the capital of Rome and Rome? No. Okay, so again. That's them. Yeah. In this book we have some weird symbols, which I don't have on my keyboard, so I cannot actually type them. So let me find that apostrophe that I couldn't type. That's, yeah, let's say we grab this apostrophe. So in our cleanup, I can replace it with the apostrophe that I can actually type. Let's run it again, and we can already see that the text that gets generated looks a bit more interesting than before. "This 'tis so," said the king, looking round the neck of the wood. "She considered him to you," said Alice sharply. Alright, so there are still some things, French music. There was something like this symbol. My god, there's so many of them. So not the best text probably, but should be fine. I think it's the same case as above. We simply use the apostrophe that is normal for our keyboards. Let's run it. The queens, croquet ground, a large rose tree stood. Okay, so what stands out to me is that there are no sentence stoppers here. Really, we see commas, semicolons, but no sentence stoppers. And this happens because the split actually removes them. So when we split text, we split sentences, the split, once it finds these characters, it removes them. And luckily for us, we can use split inclusive. So it will keep them intact. And if we run it now, Alice ventured to ask. Alice sighed wearily, said the footman, and that he shook his head sadly. Oh, I know. Alright, so this, I don't like how to call it in English, sorry. But really, if we find something, this dash, long dash, I think this one, if we grab it and try to convert it to the normal dash that I can type, like this one, then the generated text becomes better and better. Well, I hardly know no more. Thank you. I'm better now, but I'm a poor man. Your Majesty, he began. Oh, I touched some escape, I think. Alice felt dreadfully puzzled. The Hatter's remarks seemed to listen. The whole pack of cards. As you can see, the text is nonsense, so you won't find these sentences in the book themselves, but the transition from word to word, those triplets, those are actually, in a sense, the way that we speak and construct sentences. So when you type using the Markov chain, when you use touch typing, it's a bit easier to type it out than our nonsense generator before. Before that, we really had just a bunch of words that you won't even find in a real text following each other. Here, the text flows in a way that it feels like it's a real sentence. It doesn't, in most cases, it doesn't make any sense, but typing it out and practicing with this kind of generated text is so much easier. Right. So this is pretty much it about Markov Chain, about its generation capabilities. One thing I can add is that we can actually use different keys here. So right now we use triplets to find the relationship between words, where we find the first two words and store all the words that can follow this pair. But really this key could be potentially having 3 words, right? So we take 4 words, we keep first 3 as a key and keep the list of words that can follow these 3 words. But as you can understand, the longer the key, the less variation is in the text. So the less words we will find that follows this triplet. And we will probably end up with having more and more original sentences from the text or the book that you use for building the Markov chain. There is also a possibility to use a key as a single string, but that will produce much worse result, probably closer to that generate nonsense that we saw before. So this is pretty much it for today, and our last episode, I think we will try to introduce some command line arguments to our main, and maybe introduce some formatting capabilities so that we can define whether we want some predefined width or height of our text for typing session. But thank you very much for keeping up with me, and I'll see you again. Bye.